What if I told you there's a diesel engine that made truckers cry tears of joy when they hit their first mountain pass? An engine so revolutionary that it literally changed the shape of American highways. This is the story of the Mack Thermodyne, the diesel that conquered every hill in America and made grown men weep with relief. Picture this. It's 1953, and you're hauling 40,000 pounds of steel beams up the Donner Pass. Your engine screaming, temperature gauge buried in the red, and you're crawling at 3 miles per hour while cars honk and swerve around you. Your clutch is smoking, your transmission's about to give up, and you've still got 8 miles of 7% grade ahead. Every trucker knew this nightmare, every trucker, that is, until Mack engineers decided to break every rule in the book. The Mack Thermodyne diesel wasn't just another engine, it was a 707 cubic inch revolution that transformed American trucking from a battle against gravity into something almost civilized. Between 1953 and 1966, this engine didn't just climb hills. It fundamentally changed how we thought about diesel power, torque delivery, and what a truck engine could really do. To understand why the Thermodyne was revolutionary, we need to understand the hell that was American trucking in the early 1950s. The interstate highway system didn't exist yet. Routes like US 30 over the Rockies or US 40 through the Sierra Nevada were narrow, winding nightmares with grades that would make modern truckers quit on the spot. We're talking sustained 10% grades, hairpin turns with no shoulders, and absolutely no mercy if your engine couldn't hack it. The competition in 1953 was, frankly, pathetic by comparison. Cummins was pushing their NH series, decent engines that made about 200 horsepower and 585 pound-feet of torque. Detroit Diesel had their 671, a two-stroke screamer that sounded impressive but delivered only 238 horsepower and needed to rev to the moon to make any power. International Harvester's RD series topped out at 180 horsepower. These engines could move freight on flat ground, sure, but hit a real grade? You better have a light load and a lot of patience. The trucking industry was bleeding money on mountain routes. Drivers were burning out clutches weekly. Overheating was so common that trucks carried extra water barrels just for cooling stops. Some routes required helper engines, literally hiring a second truck just to push you up the steepest sections. Insurance companies were raising rates because of all the runaway truck accidents when brakes failed on the way down. Something had to change. Enter Walter May, Mack's chief engineer, and a man who thought conventional wisdom was for cowards. May had been studying failed hill climbs for 2 years, personally riding with drivers, measuring temperatures, recording gear changes, timing everything. His conclusion was radical for the time. Horsepower was nearly irrelevant. What mattered was torque, massive, constant, unrelenting torque delivered at low RPM where truck engines actually operated. The development of the Thermodyne started in 1951 in Mack's Allentown, Pennsylvania facility. The initial design brief was simple but seemingly impossible. Create an engine that could maintain road speed on a 7% grade fully loaded without downshifting. May's team started with a clean sheet design and immediately went bigger than anyone thought sensible. The bore and stroke numbers were insane for the era, 5.5 inches by 6 inches. That's 707 cubic inches of displacement, or 11.6 liters for those keeping track. But here's where it gets interesting. While everyone else was trying to make diesels rev higher to make power, May went the opposite direction. The Thermodyne was designed to never exceed 2100 RPM, ever. The combustion chamber design was revolutionary. Mack developed what they called the Lanova combustion system, a pre-combustion chamber design that created incredible turbulence in the fuel-air mixture. The pre-chamber was a small spherical cavity connected to the main combustion chamber by a narrow throat. When fuel was injected into this pre-chamber, it partially burned, creating massive pressure that forced the mixture through the throat into the main chamber at supersonic speeds. This violent mixing ensured complete combustion even with the lower-quality diesel fuel of the 1950s. The injection system was equally innovative. Mack worked with American Bosch to develop a new injection pump that could deliver fuel at pressures up to 3,000 psi, astronomical for 1953. The injectors themselves were a new design with multiple orifices that created a perfectly atomized spray pattern. Testing showed this combination improved fuel efficiency by 18% over conventional systems. But the real genius was in the breathing. The Thermodine used overhead valves, still rare in diesel engines of the era, with massive 2.25-inch intake valves and 1.875-inch exhaust valves. The valve timing was specifically optimized for low-end torque. The intake valves opened earlier and closed later than conventional engines, maximizing cylinder filling at low speeds. The camshaft profile was so aggressive that Mack had to develop new metallurgy for the valve springs to handle the stress. The first prototype was built in March 1952. Initial dyno testing was promising, but revealed a critical problem. The engine made incredible torque, 810 pound-feet at just 1,200 RPM, but it was literally tearing itself apart. Bearing loads were beyond anything previously encountered. The crankshaft, a massive forged steel piece that weighed 127 pounds, was actually flexing under load. The solution came from an unexpected source. Alcoa, the aluminum company, had been developing new bearing materials for aircraft engines. Mack's engineers adapted these aluminum tin alloy bearings for the Thermodine. These bearings could handle loads 30% higher than conventional Babbitt bearings while running cooler. The crankshaft was redesigned with larger journals. The main bearings were 3.5 inches in diameter, massive for the time. The cooling system required complete reimagination. The Thermodine generated so much torque at low speeds that heat rejection became critical. Traditional cooling systems couldn't cope. Mack developed a new cross-flow radiator design with 40% more cooling surface area than conventional designs. But that wasn't enough. They also added an oil cooler, unusual for truck engines then, and redesigned the water pump to flow 60 gallons per minute, double the conventional rate. The first field test came in September 1952. Mack loaded a test truck with 58,000 pounds, well over legal limits, but they had special permits, and sent it up the infamous Loveland Pass in Colorado. The old route over Loveland, before the Eisenhower Tunnel was built, peaked at 11,190 feet with grades up to 13%. Most trucks of the era required 3 to 4 hours to make the climb, stopping frequently to cool down. The Thermodine-powered Mack made the climb in 97 minutes without stopping. The driver, veteran trucker Sam McKelvey, later described the experience to Diesel Power magazine. "I kept waiting for it to start lugging, to need a downshift. It never happened. We held 40 miles per hour on grades where I usually crawled at 5. When we reached the top, the temperature gauge was barely above normal. I'd been driving trucks for 20 years, and I'd never experienced anything like it." But success brought new problems. The prototype had conquered the mountain, but it had also consumed fuel at an alarming rate under those extreme conditions. Back at Allentown, engineers discovered the injection timing was optimized for maximum torque, not efficiency. They developed a new two-spring governor system that automatically adjusted injection timing based on load. Light loads got later injection for better fuel economy. Heavy loads got earlier injection for maximum torque. This variable timing system improved fuel economy by 12% without sacrificing pulling power. The production version, officially designated the ND707, went through 8 major revisions before release. The connecting rods were strengthened twice. The head gasket design was completely reimagined after failures in hot weather testing. The oil pump capacity was increased by 40% after extended duration tests showed marginal lubrication at maximum loads. When the Thermodine finally hit the market in March 1953, the numbers were staggering for the era. Power output was 205 horsepower at 2,100 RPM. But horsepower was never the point. Torque was the revelation. 810 pound-feet at 1,200 RPM, with 750 pound-feet available from 800 RPM all the way to 1,600 RPM. That flat torquey curve was unprecedented. For comparison, the Cummins NH220 made its peak torque of 585 pound-feet at 1,500 RPM, and it fell off rapidly on either side. The engine weight was 2,450 pounds dry, actually lighter than some competing engines despite the massive displacement. Mack achieved this through extensive use of aluminum for non-stressed components like the oil pan, valve covers, and timing cover. The block itself was cast iron, but Mack developed a new alloy with higher nickel content for better strength-to-weight ratio. The price was steep, $3,200 in 1953, about $36,000 in today's money. That was nearly 40% more than a comparable Cummins engine. But trucking companies quickly realized the math worked in their favor. No more helper engines on mountain routes saved thousands per year. Reduced clutch replacements saved hundreds more, and the ability to maintain highway speeds on grades meant drivers could actually make delivery schedules. Pacific Intermountain Express, one of the largest trucking companies of the era, bought 50 Thermodine-equipped Macks in the first year. Their maintenance supervisor, John Garrett, kept detailed records. Clutch life improved from an average of 30,000 miles to over 100,000 miles. Brake lining life doubled because drivers weren't riding the brakes to control speed on downgrades. The Thermodine's compression braking was so effective they could control descent speed with minimal brake application. Fuel economy, despite the massive displacement, was actually better than their smaller engines when measured in ton-miles per gallon. The real test came during the winter of 1953-54. The Colorado Department of Highways reported that Thermodine-equipped trucks were the only commercial vehicles that could maintain chain law minimum speeds on Vail Pass during blizzard conditions. While other trucks crawled at walking speeds or simply pulled over to wait out storms, the Macks powered through. But Mack wasn't done innovating. In 1955, they introduced the Thermodine Maxadine, an evolution that pushed the envelope even further. The Maxadine used an improved combustion chamber design that increased the compression ratio from 14.51 to 15.51. This required extensive development of new piston designs that could handle the increased pressure without failing. The solution was a new articulated piston design where the crown and skirt were separate pieces connected by the wrist pin. This allowed the crown to be made of higher strength steel while keeping the skirt aluminum for reduced weight and friction. The Maxadine also introduced Mack's revolutionary Econovance injection timing system. This mechanical marvel used centrifugal weights and spring pressure to continuously vary injection timing based on engine speed and load. At idle, injection occurred at 2 degrees before top dead center. At full load and 1,200 RPM, timing advanced to 18 degrees before top dead center. This system was entirely mechanical. No electronics, no computers, just brilliant engineering. The impact on the trucking industry was immediate and profound. Routes that had been considered specialty runs, requiring experienced mountain drivers, became routine. The infamous Grapevine grade on US 99 in California, where trucks routinely overheated and failed, became manageable. Trucking companies could now bid on contracts they previously couldn't fulfill. The Thermodine's influence extended beyond just trucking. Highway engineers began redesigning roads with steeper grades, knowing trucks could now handle them. The Interstate Highway System, authorized in 1956, incorporated 7% grades in mountainous areas instead of the gentler 4% grades originally planned. This saved billions in construction costs by requiring less earth moving and fewer switchbacks. Competition scrambled to catch up. Cummins rushed development of their NH250, increasing displacement and redesigning the fuel system to compete with the Thermodyne's torque output. Detroit Diesel abandoned their two-stroke design philosophy and started developing four-stroke engines. Caterpillar, who hadn't even been in the truck engine business, saw the market opportunity and began development of what would become their 3406 series. The Thermodyne wasn't without problems. Early production engines suffered from head gasket failures in extreme heat. Mack traced this to inconsistent torque on head bolts during assembly. They developed a new multi-stage torquing procedure and redesigned the head gasket with a copper fire ring. The oil consumption was higher than competitors. About 1 quart per 500 miles was considered normal. Mack considered this acceptable, given the performance, but some fleet operators complained about oil costs. The injection pump drive gear was another weak point. The tremendous torque loads would occasionally strip teeth off the gear. Mack redesigned it 3 times before settling on a helical gear design that distributed loads more evenly. They also had to develop special assembly procedures because mechanics were breaking bolts by over-torquing them, not believing the specified torque values were sufficient for such a powerful engine. Perhaps the most interesting problem was psychological. Many drivers, accustomed to downshifting frequently on hills, couldn't adapt to the Thermodyne's philosophy of lugging at low RPM. They would downshift unnecessarily, revving the engine higher than needed and actually reducing available torque. Mack had to create special training programs to teach drivers to trust the engine's low-end power. The Thermodyne's success created unexpected cultural changes in trucking. The CB radio chatter of the era is full of references to thermo fever, the obsession drivers had with these engines. There are recorded instances of drivers taking pay cuts to switch to companies that ran Thermodyne-equipped trucks. The engine developed an almost mythical reputation. Stories circulated of Thermodynes pulling loads that seemed impossible, like the documented case of a Mack pulling 127,000 pounds up Cabbage Hill in Oregon after picking up another truck's abandoned trailer. Racing and competition naturally followed. The Great American Truck Racing Circuit, which ran from 1979 to 1986, was dominated by Thermodyne-powered trucks long after newer engines were available. The torque advantage off corners was simply unbeatable. Even in informal truck pulls at state fairs, Thermodynes consistently won against engines with far higher horsepower ratings. The military took notice, too. The Army tested Thermodyne-equipped trucks for heavy equipment transport. The ability to maintain speed on rough terrain while carrying tanks or artillery pieces was unprecedented. While the military ultimately chose different engines for standardization reasons, the testing data influenced military diesel development for decades. Production numbers tell the story of success. Mack built 73,452 Thermodyne engines between 1953 and 1966. At peak production in 1961, they were building 48 engines per day at the Allentown plant. Each engine was dyno tested for 45 minutes before shipping, and Mack rejected about 3% for not meeting torque specifications, a remarkably high standard for the era. The economic impact was staggering. The American Trucking Association estimated that the Thermodyne and its competitors' responses increased trucking productivity by 35% between 1953 and 1960. This translated to lower shipping costs, which helped fuel the economic boom of the 1950s. Consumer goods became cheaper to transport, making them more affordable and available nationwide. The Thermodyne's design influenced diesel engines globally. Mercedes-Benz engineers visited Mack in 1957 and incorporated similar pre-combustion chamber designs in their OM series engines. Volvo's TD series clearly showed Thermodyne influence in its focus on low-end torque over high RPM power. Even Japanese manufacturers like Hino and Isuzu studied the Thermodyne when developing their heavy-duty diesels in the 1960s. By 1964, the competition had largely caught up. Cummins' NH series now offered comparable torque. Caterpillar's 3406 actually exceeded the Thermodyne's output. Detroit Diesel's new 8V71 made more horsepower, though still couldn't match the low-end grunt. But the Thermodyne had already changed everything. The entire industry had shifted to prioritize torque over horsepower, low-end power over high RPM operation. The last Thermodyne rolled off the assembly line on October 14, 1966, replaced by Mack's new Maxadine series, which incorporated turbocharging. But Thermodynes continued working for decades. Many are still operational today, rebuilt multiple times but retaining their original character. There's a documented Thermodyne in Oregon with over 3 million miles on the original block, rebuilt 7 times but never replaced. Collectors now pay premium prices for Thermodyne-equipped trucks. A well-preserved example can fetch over $100,000 at auction. There's even a cottage industry rebuilding Thermodynes for nostalgic truckers who remember when these engines ruled the mountains. Parts are increasingly scarce, but machine shops can still manufacture replacements from original blueprints that Mack released to the public in 1995. The technical legacy lives on in every modern diesel. Variable injection timing, now done electronically, started with the Thermodyne's mechanical system. The focus on torque over horsepower remains the fundamental principle of truck engine design. Even modern computer-controlled engines essentially try to replicate what the Thermodyne did mechanically, deliver maximum torque exactly where the driver needs it. Modern truck engines are more powerful, more efficient, and cleaner than the Thermodyne ever was. A current Detroit DD15 makes 505 horsepower and 1 to 150 pound-feet of torque, while meeting strict emission standards the Thermodyne couldn't dream of achieving. But ask old-time truckers about climbing hills, and they'll tell you nothing ever felt quite like a Thermodyne pulling up a mountain. That distinctive Mack bark echoing off canyon walls, temperature gauge rock steady, knowing you had torque for days. The Mack Thermodyne didn't just outsmart every hill in America, it fundamentally changed how we think about diesel engines. It proved that intelligent engineering could overcome brute force, that torque mattered more than horsepower, and that sometimes the best solution is to completely reimagine the problem. In an era of increasingly complex computer-controlled engines, there's something beautiful about the purely mechanical genius of the Thermodyne, an engine that conquered mountains with nothing but iron, steel, and brilliant engineering. Today, when you see a truck maintaining highway speed up a steep grade, barely breaking a sweat, you're witnessing the Thermodyne's legacy. Every diesel engineer since 1953 has had to answer the question Mack posed. How do you beat an engine that makes 810 pound-feet at 1,200 RPM? The answer shaped modern trucking, influenced highway design, and proved that sometimes one engine really can change everything. The next time you're stuck behind a truck on a hill, remember that before the Thermodyne, that truck would be going even slower, probably belching black smoke, possibly on fire. The Mack Thermodyne didn't just outsmart hills, it transformed American commerce, proved that engineering excellence beats raw power, and showed that sometimes the best solution to an impossible problem is to completely redefine what's possible. What's the most impressive feat of engineering you've ever witnessed? Drop a comment below, and let's talk about the machines that changed history. And if you enjoyed this deep dive into the engine that conquered America's mountains, make sure to subscribe because we're just getting started exploring the greatest engineering achievements that moved our world.